Welcome to Variation Part 2. Consider the sample 2, 4, and 9. We're going to want to put that in our list and run one var stat. You should be pretty good at that by now. Here's the outcome I got. What we're really interested in this video are these two values right here. Sample standard deviation and population standard deviation. Hope you don't mind if I abbreviate a little. To calculate these by hand is a real pain. But let's look. If we put our data in a column, and then we calculate the mean. So I add these guys up, divide by how many numbers I have. That's my mean. We'll call it my sample mean, or x bar. So I'm going to subtract my mean from each value. That gets me -3, -1, and 4. Then we want to take those values and square them. That gives me 9, 1, 16. Now, if I'm doing sample standard deviation, I add those guys up, I divide by 1 less than how many numbers are in my list. I have 3 numbers in my list. 1 less, subtract 1. And that gives me variance, sample variance. That would be 26 over 2, or 13. Variance is a pretty useless value to know. However, the one thing it's good for is, when you take the square root of variance, you get standard deviation, and that's a very valuable calculation. So the square root of 13 that's 3.60555. I would round to 56, and sure enough, that's exactly what our calculator told us it was. If we were going to do population standard deviation, we would have to calculate population variance first, and we do everything exactly like we did. However, this time we don't subtract 1 off from that denominator. We just leave it with the sample size of 3. That's lowercase sigma squared, which is 26 over 3, not quite as nice a number, 8.67 if I round. When we take the square root, if I didn't round, we'd get the exact number our calculator got. But since I'm rounding, I'm going to get 2.9445. How close did I come? Not too bad. But those rounding errors can really hurt you in stats. So you want to wait until the very last thing to do your rounding. If I took the square root of 26 over 3, now I'm going to round to 2.9439. Why the heck do we subtract that 1? Well, let's think about this. If I had all of my students' statistic papers and every possible grade a student made, I have some students that didn't ever turn in a paper. They got a 0 on it. I have a lot of students that scored in the 75 range. Not too many hundreds. We'll say if I had a bar graph, it might go something like that. That's every single statistics paper. Now, let's say I take a random sample of 30 of those. I have very few 0 scores, and I don't have too many 100 scores. What are the chances that I get a 0 paper and a paper with 100 on it in my sample? Not too good. I'm probably going to get lots of my papers in the 60 to 90 range. But that's not as big a range as my actual population has. So when I calculate my standard deviation on a sample, it's going to be far less spread out than on my actual population. We have to compensate for that. When we compensate for that smaller range, we do that by adding, that's the sum symbol, our data values, which we usually call x for a random variable, minus our sample mean, square that quantity, and divide by the sample size minus 1, and then take the square root. Whereas if you're doing population, you've got the entire range, and you don't have to compensate with that minus 1 guy. And that's the difference between sample variation and population variation. Sample standard deviation and population standard deviation. My math lab will ask for variance. It assumes you're doing this by hand, and you would have to calculate your variance before you got your samples, before you got your standard deviation. Since we're probably always going to use our calculator to calculate standard deviation, when we get that value, Sx or sigma x, out of our calculator, we're going to have to square it. So if I take 3.6056 squared, that's going to give me a really good estimate of sample variance. Notice those rounding errors are going to kill you. So I would carry the number all the way out. Put every digit that your calculator gives you for S of S when you square it, and then round after you've squared. And that's it for standard deviation and variance. How cool was that?